So what we're gonna try to do today is we're going to find the area using what's called the limit process. Area. So the limits process. And this is gonna get pretty down and dirty in terms of the algebra and keeping track of stuff. So if I start going too fast, slow me down and make me explain, because it's easy to get lost in all the stuff we're gonna do here. But big picture, this is going to be the third of 4 ways we're going to have of eventually evaluating our definite integral. So this is the big focus of integral calculus. The second half of calculus is how do you evaluate these integrals and what are the applications and that come from that. So far we have what we have called the area argument. So if I give you a very carefully selected graph or a function like a semicircle where you know what the geometric figure is, so for example, if we do something like the integral from -2 to 2 of the square root of 4 minus x squared dx, we don't really have much of a chance of trying to do anything with this unless you can recognize that the graph of that is actually a semicircle of radius 2. So if you knew what that was, or you were told what it was, and you recognize that it's a semicircle, then we know that the area of a circle is pi r squared. So a semicircle is going to be 1/2 pi r squared. Then we could recognize that the radius is 2, 2 squared is 4, half of that is 2, and so this would be 2 pi. And since this curve is completely above the x-axis, then its integral will be actually the area. And so we could know then that the value of this integral is 2 pi. So that's one way, but it's pretty limited in its application because it depends on you either being given a graph of a function that you can actually figure the area of, or an equation where you know what the area of that geometric shape is. But it's one that we still take full advantage of, and you'll for sure see some on the AP exam where you're going to be given some kind of graph, and it may be that you have some straight line segments and semicircles and so on, and you're going to piece together how to evaluate the integral by computing the area of various parts of that graph and recognizing, when they're above the x-axis, it's going to be positive, and when it's below the x-axis, they're going to be negative. So that is an important idea. The second one that we have done is using our calculator and df and integrate. And that also is a must-have skill. So you will for sure have to evaluate and answer some questions using your graphing calculator to find some integrals that there's no way you could get any other way. And they're going to be so complicated that you'll be like, I don't know how to do this. Oh, that's why it's appearing in the calculator active portion of the test. This is going to be a third one, and it's pretty limited in how much we're going to see on it. It's going to be a conceptual thing. So what I'm going to do is we're going to look at an area under a curve, and we'll look at a Riemann sum that we know will be an underestimate and a Riemann sum that we know is going to be an overestimate. And we're going to compute it using this idea of the limit process each of those ways. And so the one that we know is going to be an underestimate and the one we know is going to be an overestimate, when we take the limit as n goes to infinity, if we do this right, we're going to get the same answer, which is going to then hopefully be a convincing argument that it doesn't really matter how you set up your Riemann sum if eventually you're going to take the limit as n goes to infinity and get the exact answer. That it really does equal what that integral is. Okay, so that's a long-winded start to this. So, maybe let's first talk a little bit about summations and make sure we understand how these things work. So, these summations are these big sigmas. So it doesn't matter what you call this, so I'm gonna make these very simple at first, so we just kind of get the feel for it. If we go sum I going from 1 to 3, and we do something like I squared plus 1, then what that means is you're going to start at the starting value, and you're gonna plug that in for whatever that variable is, and it can be whatever. So we plug in 1 for I, and so we go 1 squared plus 1. That's the first term. And then we go plus, that's what the summation indicates. That always, once you have evaluated at that value of I, then you're gonna add the next term. So then you bump the I always up 1, never fractions. So you bump the I up 1, now it's 2, and you plug that in. So it becomes 2 squared plus 1. Plus, and then you bump it up, and you keep doing this until you get to the upper limit. And that is the last one you're gonna plug in. You do plug it in, and that's gonna be the last term. So that's gonna be a 3 squared plus 1. So that's how that works, and then we just actually evaluate them. So 1 squared is 1, plus 1 is 2, 2 squared is 4, plus 1 is 5, 3 squared is 9, plus 1 is 10. So we would say that that's equal to 17. Is that okay? And you can, like I said, you can start anywhere you like, and it doesn't have to always be i's. So commonly it's I, J, K, N that you see. So if I said K was, say, -1 to +2, and we did something like 2K plus 1. So what that tells us is we would start with -1, so we would get 2 times -1 plus 1. And there's our first term. Plus, and we include 0, so it's going to be 2 times 0 plus 1. Plus, and then we get 2 times 1 plus 1. Plus, and then the last one that we put up there, the upper limit is 2, so that's the last one we plug in, 2 times 2 plus 1. So then we just do what it says, 2 times -1 is -2, plus 1 is -1, 2 times 0 is 0, plus 1 is 1, 2 times 1 is 2, plus 1 is 3, 2 times 2 is 4, plus 1 is 5, and the 1's cancel, so it's going to be 8. Does that make sense so far? All right. So, we are also going to make use of, as we do this, we're going to make use of some different formulas. You do not have to memorize these. I'll always give them to you, but on the homework sheet that I just handed out, the Larson worksheet, on the very front page, you will see in a box there, it says Theorem 4.2, the summation formulas. You with me there? And so it's saying that what the first one is saying, and I won't really use this one very much because I think it is kind of self-explanatory, the first two, first one. So what this is saying is that if you have some constant, say you had the sum I going from 1 to n of 5. So what that means is you're going to add 5. I mean, there's no place that this I gets incremented. It doesn't appear anywhere in there. So when I is equal to 1, you get just 5. Plus. Now I becomes 2, and you still have 5. Plus. See how this is working? And you keep doing this until you get to the nth one. So how many 5s do we have? N. So what would their sum be? 5n. Now you add 5n times. And so that's what that first formula is saying. And I'm not going to really use come up sometimes, we'll see, but I think we can just kind of reason our way through it without having to resort to a formula. Now, the second one is the sum of the i's. So when you read across there, it's saying the sum I going from 1 to n of I is n times n plus 1 all over 2. So there's kind of a famous story, I don't know if this is true or not, but it's attributed to Gauss, who was a brilliant French mathematician in the 1700s, I think. So the story goes that, Gauss, of course, was brilliant. So when he was a little kid, you imagine in elementary school, and, you can visualize some poor elementary teacher trying to corral these, I don't know what they had, 20, 25, 30 kids, and keep them busy and on task. And this is, of course, why I don't teach elementary, because, they have an attention span of a flea. And so, so here's Gauss, who, of course, is brilliant. And so no matter what the poor teacher gives them to do, he's got it done like that, and then needs something else to do to keep him busy. So the teacher at wit's end says, oh, just go add up the first 100 numbers. And so it's what this is representing, 1 plus 2 plus 3 up to 100. So Gauss goes off and comes back a few minutes later and says, oh, it's going to be this. It's just going to be 100 times plus 100 times 101 divided by 2. What did you do when you were in elementary school is the question. So, you can see he was pairing them up, that you're gonna, there's gonna be 101, and 99 plus 2 is 101, and that's, how he is coming up with that. There'll be 100 divided by 2 will be 50 pairs, and each of those will be 1 plus 101. Not bad for elementary school. Anyway, you don't have to come up with one of these, you just have to be able to use it. The one we will make a lot of use of is the sum of the I squared. I going from 1 to n of I squared, so that means 1 squared plus 2 squared all the way out to n squared. And it says the sum of those squares is going to be n times n plus 1 times 2n plus 1 all over 6. Okay? We'll come back to that in a moment. You don't have to memorize these or anything, just figure out how to use them. So here's our challenge. We're going to look at the function f of x equals 9 minus x squared. And we are going to talk about the interval from 0 to 3. So we are going to try to evaluate, this definite integral from 0 to 3 of 9 minus x squared. And we're going to use the limit process. So there's a picture that goes with this. We know what 9 minus x squared looks like. It's going to be a parabola that opens down. Its vertex is at 0, 9. So we're going to have, there is going to be 0, 9. And it's going to be a parabola. We're not really interested in the part that's going off there to the left. And so I'm not going to really draw that in dark there. We know that at 3, 9 minus 3 squared 9 is 0. So that's where we intersect the x-axis. And so we're talking about trying to find this area between this parabola and the x-axis in quadrant 1. Does that kind of make sense? Now you can look at that and see, because this is a decreasing function, we talked about this a little before, but it gives us a chance to revisit that. If we take left rectangles, so a left Riemann sum, if we imagine what that would look like, so if we were going to use n rectangles, and we would, and we're going to make these be uniform width. So I'm just going to draw a few of them. So you can see, is that left Riemann sum going to be an overestimate or an underestimate? It's going to be overestimate, right? So I'm going to say, I'm going to call that a capital F sub n, and we know that that has to be greater than or equal to the true area under the curve. And because our curve is non-negative, that is in fact equal to that integral from a to b of f of x dx. You okay with that so far? Then, so I'm gonna come back to that one. I think it's easier to conceptualize what we're about to do here using right rectangles. So I'm gonna start with this one. But a right Riemann sum means we are going to use right rectangles. So as we draw those, if we use the right side of the subinterval, the right side of that delta x, then is that going to be an overestimate or an underestimate? If you could see it, Katie, would that be an overestimate or an underestimate?
It's an underestimate.
It's an underestimate. So I'm going to call that a little less of n, and that's going to be less than or equal to the true area under the curve, which again is our integral from a to b of f of x dx. So what I'm going to propose to do here, what we're going to try to do, is I'm going to start with the right Riemann sum because I think conceptually it's just a little easier to wrap your head around. I'm going to start with that, and we're going to write this all out and get an expression for n rectangles. And we know that that's going to be an underestimate. Then we're going to take the limit as n goes to infinity. We're going to evaluate that limit, and we're going to get an actual number, because that limit will exist. Then I'm going to kind of put that number aside, knowing that that number has to be less than or equal to the true area, which is our integral. Then I'm going to come back, and we're going to redo the whole thing using a left Riemann sum, which we know is going to be an overestimate. And we're going to work through all the details again, and we're going to get an expression, and then we're going to take the limit as n goes to infinity. And if all goes well, it will be amazing, because we will hopefully get that this will be the same number that we got there. And since our area, which is the integral, has to be in between those, that means that must in fact be the true area. That's the reason. And then what the takeaway is, it doesn't really matter how you set up your rectangle. Left Riemann sum, right Riemann sum, midpoint Riemann sum. Once you take the limit as n goes to infinity, that's going to be the exact value. So when you get asked to do this, when you're asked to evaluate an integral using the limit process, which you will be, then I would always just choose a right rectangle to set up because I think it's easier. Because once you take the limit, it's not going to matter anymore. Okay? All right, here we go. So we're looking at the purples. Now, we're going to say that we're going to take uniform width rectangles. So our delta x is going to be b minus a over n. They're all going to be the same width. And so in our case, this b minus a over n is going to be what's b and what's the a? B is 3, a is 0. So it's going to be 3 minus 0 over n. That's going to be 3 over n. Okay? That's our delta x, and they're all the same for all the rectangles. Okay, so what our claim is that our area is going to be approximately equal to, and I'm going to try to write out an expression for n rectangles. So we're dividing this interval from 0 to 3 into n subintervals of equal length, and we're going to find the area of each of those rectangles. So that means our first rectangle is going to be the function evaluated at the right side of that subinterval. The right side of that subinterval. So if you can visualize here, there is the right side of our first subinterval. That's the right side of our first rectangle. What is that number? Oh, Ainsley, that's brilliant, right? It's 1 delta x over, and delta x is the 3 over n. So it's from 0, we've gone over 3 over n. So that's going to be f of 3 over n. Now, for reasons that will become clear for counting purposes, I'm going to say it's 3 over n times 1. That is 1 delta x from 0, our left endpoint. Okay, and then that's the height. The width, or the base, either way, of our rectangle is gonna be
3 over n.
3 over n, it's that delta x, right? This width right here is our delta x, which is 3 over n. So that's gonna be times 3 over n. There's the area of that first rectangle. We good to go? He nods of heads. Okay. Second rectangle. We're gonna take f of, well, what are we gonna plug in to the function to get the height of our second right-hand rectangle? We're gonna plug in that x value right there, and that's how far away from 0?
3 over n times 2.
Yeah, 3 over n times 2 is 2 delta x's, right? And each one is 3 over n, so it's 2 times 3 over n. I'm not gonna write it as 6 over n, even though that's what it is, for counting purposes, because I'm gonna lead up to a formula here in a moment. So I'm gonna say it's f of 3 over n times 2. Is that making sense why I'm doing that? Okay, times its width, or base, which is
3 over n.
also 3 over n. Okay, let's do one more, and then we'll go run out to the nth one. So the third rectangle is going to be f of
3 over n.
3 over n times 3 times the width, which is
3 over n.
3 over n. Plus, okay, now we're gonna run it out to, we're out to the nth rectangle. Okay, here we are, over here somewhere, and we have our, it's a right rectangle. So, well, there it is. Because we're using the right side as the height, but that's okay. We know it's gonna be 0, but it's gonna be f of, we're gonna write it for counting purposes as f of
3
3 over n times n, right? Which is 3, I know, but we're gonna call 3 over n times n, times its width, which is 3 over n. Okay, now the algebra begins. So, all of these had a common factor of 3 over n. I'm gonna pull them out. There's the 3 over n, big bracket. Okay, so now we've got inside here f of 3 over n times 1 plus f of 3 over n times 2 plus dot, all the way out to f of 3 over n times n. Does that seem reasonable so far? Okay, now we're going to evaluate these. So we're going to take these 3 over n times 1 and all those, and we're going to plug them into our function, the 9 minus x squared. Okay, so we got 3 over n times, so if we plug 3 over n times 1 in for x, this is going to be 9 minus, I'm going to go parentheses 3 over n times 1 squared. Okay? There's 9 minus 3 over n times 1 squared. That is just the height of that first rectangle, yes.
Why is it squared again? Oh, because
That was just the function I made up. Yeah, that's our parabolas opening down. Is that okay so far? Now, that's the first one. Now, the next one is going to be plus. So now we're plugging 3 over n times 2 into our same function. So that's going to look like what?
9 minus 3 over n times 2 squared.
Perfect. Let's do one more. Then we'll run out to the nth one. So here's our third rectangle. So this is our second rectangle. Now our third rectangle is going to be 9 minus 3 over n times 3 squared. And here's our nth rectangle. You ready for it?
9
9
minus
minus,
3 over n times n squared.
okay, nice. Okay, now, here's where you could use that formula, but I think we can just logic our way through it. We have each of these expressions, each of these areas of rectangles has a 9 in it. So there, if I kind of skip over this stuff, we have a 9, another 9, another 9, all the way up to that. How many 9s do we have? N of them, one for each of the n rectangles. If we add 9 plus 9 plus 9 n times, we get a total of 9n. I'm I'm adding them all up and I'm putting them right in the beginning. There's all those nines added together. Does that make sense? Now, all these other terms, so now we're ignoring the nines because we took them out of the mix. All of these others have a minus sign in them. True? I'm gonna factor that out. So I'm gonna go minus, parentheses. Is that okay so far? Now, each of these, we have a product of two things squared. We have a 3 over n times 1 quantity squared. When you have two things that are multiplied together and raised to a power, each of those gets raised to that power. So the 3 over n is going to get squared, and the 1 is going to get squared, and they'll be multiplying each other. So the 3 over n squared, the 3 over n quantity squared is going to be 9 over n squared times,
1 squared.
I know it's, you don't want to call it 1 squared for counting purposes. Is that okay? Plus, because I factored the negative out, so now it's plus. This one is going to be what? 9 over n squared times 2 squared. With me? Plus, let's do the third one. 3 squared. Now we're running out to the nth one. 9 over n squared times n squared and parentheses and bracket. Okay? More algebra. Everything in the parentheses has a common factor of 9 over n squared. We're going to pull it out. So it's going to come out and join that negative sign. Minus 9 over n squared. With me? Now what's in the parentheses is 1 squared. Good. It's 3 squared. All the way out to n squared. Nice. Okay. Now is where we're looking at that formula. So we've maneuvered this intentionally to get to this place. This stuff right here, at 1 squared plus 2 squared, 1 squared plus 2 squared, all the way out to n squared, is the sum of I squareds, I going from 1 to n. See it on your formula sheet. So all of these things, these n squares being added together, according to that formula sheet, we can replace by n times 2n plus 1. No, is that right? N times n plus 1. Is that right? 2n plus 1?
No.
No. Did I get that right? Yes. Okay. So that's what I'm going to do. I'm going to replace all that stuff by its formula. Okay, we're getting there, guys. We have 3, I'm going to stick with the white here. We have 3 over n, bracket 9n minus 9 over n squared times, and now all those sum of squares gets replaced by n plus 1, 2n plus 1, all over 6. Okay? Now, at this point in time, if we wanted to get an actual approximation to the area of the curve, we could plug in a value for n. If you said, let's do 10 rectangles, we could plug in 10 for all of those n's, throw it on our calculator, and we get an approximation. And then we say, we want a better approximation. Better means more rectangles. We could choose n to be 100, and we could plug 100 in for n, throw it on our calculator, and we would get a better approximation. We're not going for better, we're going for best. So we're going to take, the limit as n goes to infinity. Okay? Before I do that, I'm going to distribute a little bit here. Okay? So we have this 3 over n outside the bracket. Inside the bracket, there's really 2 terms separated by the minus sign. There's this term, just the 9n, minus, and then there's all this stuff right here is just 1 term. So I'm going to distribute that 3 over n times each of those terms so I can get rid of the brackets. Is that okay? So 3 over n times the 9n, well, the over n and the n are going to cancel. We're just going to get 3 times 9, which is 27. Now, these things here, this formula and the times 9 over n squared, these are multiplying each other. So when we introduce this 3 over n, it's not going to distribute. It's just going to hit this first term, which is going to carry it as we continue with the multiplication in a bit here. So the 3 times the 9 is gonna make that be 27. The over n times the over n squared is gonna make that an over n cubed. And that's gonna be, and I don't know if you want the multiplication symbol or not, there's our n plus 1, 2n plus 1 all over 6. Is that okay? Now, we are going to take the limit as n goes to infinity. I love doing this because I like to think of this as now we can do fuzzy math. So we don't have to get real involved here. If we multiplied out n times n plus 1 times 2n plus 1, which I have no intention of doing, if we did, we would get something with an n cubed in it. Eventually we get something with an n squared, something else with an n, and there'd be a constant. Probably not a constant because that n would multiply. But I don't really care because as n goes to infinity, what is going to matter out of this expression? Only the largest power. Does that make sense? So something is going to be n cubed there. The n squared and the n terms compared to the n cubed as n goes to infinity is insignificant. So I don't care. I'm not worried about it. So I'm just going to pick the highest power of n and its coefficient out of this expression. So this is going to go to, well, we still got the 20, keep the limit as n goes to infinity. We got the 27, doesn't have any n's in it at all. So as we multiply out this n times 2n plus 1, what is the n cubed term is going to have what for a coefficient? 2, right? It's going to be a 2n cubed. See it? Times the 27 is going to be 54n cubed. The rest of it, it's insignificant. So that's going to be a 54n cubed. In the denominator, we're going to get just the 6n cubed. This is the essence of what's going on here. This is the important stuff in terms of the limit as n goes to infinity. Well, you can do this. So we have, well, as n goes to infinity, 27 is just always 27. It doesn't matter what n does. That's going to be 27. The n cubes, they're going to get huge, but at the same rate. So as we put in a million, a billion, a trillion, those cubes are the same thing. They're going to cancel each other out no matter how big the n's get. 54 divided by 6 is,
9.
and so we're going to get 27 minus 9 is 18. That's our limit. Now, remember, we said this was an underestimate. So we have that 18 is less than or equal to this integral from 0 to 3 of 9 minus x squared dx. That make sense? So I'm going to erase all this stuff, and now we're going to go back and repeat the process, but we're going to do a left Riemann sum, which is a lot like a right Riemann sum, only not quite as much fun. Okay? Okay. So, showing the evidence, all that work just to get erased, just go to my life. Okay, now, the left Riemann sum is just a little more awkward. So, that's why, given the choice, I pick right Riemann sums. So, we're gonna, again, say our area is gonna be approximated by, and we're going to try to find an expression for these n rectangles. But now we're gonna do left rectangles, okay? So that first rectangle is going to be f of, well, let's see. Now we're on the left side. So the left side of that first rectangle has an x value of 0. Well, I'm going to think of it as being 0 delta x's to the right. So for numbering purposes, I'm going to call it 3 over n times 0. Is that okay? okay or not, that's what I'm gonna do. So I'm gonna call that 3 over n times 0. Times its width, which is still gonna be 3 over n. Now, the second rectangle is gonna be f of 3 over n times 1. Okay, so we're gonna be off by 1 each time. The first rectangle is 0 delta x's over. The second rectangle is gonna be 1 delta x over. We're always gonna be trailing by 1 here. And our width is gonna be 3 over. Let's do another one. The third rectangle is gonna be f of
3 over n times 2.
times the 3 over n. Now, it gets a little more awkward still. Now we're at the nth rectangle. So now we're using that left side. So we are going to be, I think we're going to this pen, but I think it's better. It's going to be f of 3 over n times what? Exactly. We're 1 short of n, right? Which is n minus 1. And I told you, you weren't going to like this as much. Times our width, which is 3 over n. Is that okay? Okay, well, here we go again, doing our algebra. We're going to pull out the 3 over n's. 3 over n, big brackets. And now, should we jump right to plugging them in? So we're going to plug into our function 3 over n times 0. And our function is still 9 minus x squared. So we're going to get 9 minus 3 over n times 0 squared. Is that okay? There's our first rectangle. Okay. Plus 9 minus 3 over n times 1 squared. Let's do our third one. Plus, what is it?
Minus 3 over n times 2 squared.
Nice. Running all the way out to that nth rectangle, which is going to be 9 minus, this is going to be ugly, 3 over n times the n minus 1 squared. Okay? All right. Well, you know the drill. We're going to add up all the 9s. How many 9s do we have? N of them. Their sum is going to be 9n. Now we're going to factor out the minus. Should we go ahead? Can we see, since we did this once before, what's our common factor out of all these going to be? 3 over n squared, which is going to be 9 over n squared. Is that okay? So I'm going to go minus 9 over n squared times. Now what's left behind is 0 squared plus 1 squared plus 2 squared all the way out to n minus 1 squared, in parentheses and bracket. Okay, so this is, I'm going to come up over here. So we've got our 3 over n times 9n minus 9 over n squared times. Now, the 0 squared here, I'm going to say, well, 0 squared is 0. I'm not going to count that. So I'm going to think of this as going 1 squared plus 2 squared out to n minus 1 squared. So that's the sum of the first n minus 1 squares. So in our formula, we have the sum of these I squared. I is going to go from 1 to how much? N minus 1, not all the way to n this time. We're 1 rectangle short from where we were. 1 square less than we were before. Does that make sense? You see that okay, Taylor? That's an n minus 1 on the top. I'll rewrite it up here. So we've got summation I going from 1 to n minus 1 of those I squareds. That's going to generate that 1 squared plus 2 squared all the way out to n minus 1 squared. Okay, well, our formula says that this is going to be, I'm going to destroy some of this here. So our formula said that was going to be n times n minus 1 times 2n plus 1 all over 6. Where we started from 1 and went to n, but now we're going to n minus 1. That means each of these n's in that formula, we're going to replace with n minus 1. Okay, so our formula is going to be, that n is now going to be n minus 1. That n minus 1 is now n minus 1 minus 1, it's n minus 2. Now this 2 times n is now going to be a 2 times n minus 1 plus 1. So that's 2n minus 2 plus 1. That's 2n minus 1. There's our formula adjusted for our upper limit of n minus 1. You okay? Okay, so our formula now looks like n minus 1, n minus 2, 2n minus 1, all over 6. Now, in the finite case, if you wanted to make an approximation, you could plug in whatever finite number for n. You want to know what would your approximation be with 20 rectangles? Plug in 20 for n. 50 rectangles, plug in 50 for n. But we're going for exact. So we are going to take a limit and then goes to infinity. So I'm going to do again, I'm going to distribute this to the two terms. That 3 over n is going to go to each of those, and then that will carry it forward with the multiplication. So on the first term, 3 over n times 9n is going to be 27, because the n's are going to cancel. You okay? It's going to be a minus 27, n minus 1, n minus 2, 2n minus 1, all over 6n to the third. Okay? So here again is where I love the fuzzy math. You okay, Zane, with that? Okay, so the fuzzy math is, we don't sweat the small stuff, right? As n goes to infinity, all that's going to matter is the highest power of n and its coefficient. So without actually multiplying it out, we can see what's going to emerge from all of this mess is going to be 7 cubed again, right? 2n cubed times that 27. We're going to get, and room for a limit still. So we have our 27 minus, that's going to be 54 n cubed over 6n cubed. This looks familiar, doesn't it? So again, those are going to cancel. That's 9. We get 27 minus 9. We get 18. How about that? So we're saying that that area, that integral, must be in between 18 and 18. That's pretty restrictive. Okay, that's the true area under the curve. So you are going to have to be able to do this, and then because if we're going to use the limit process, it doesn't make any difference how you set up your integral, left Riemann sum, right Riemann sum, whatever. So I would always personally choose the right Riemann sum. I think it's just easier to conceptualize. You start your first rectangle with 1 rather than 0, and you end at n rather than n minus 1, which just makes the whole thing flow a little bit better. Is that okay? All right. I don't know, 10 minutes enough for you to do one on your own? Oh, yes, I'm hearing you would like to try one on your own. We will try, half of that equals x squared plus 1, and we'll go from the interval 0 to 2. Anybody bold enough to try that at the board? No, I'm hearing, that's okay. You start on this. I'm going to, I really want to check some homework. So I'm going to turn off the video because I'm telling me not to include you in the video, I don't think I'm supposed to do that, so. I'm gonna turn this off, but then I'm gonna come around and check your homework. I feel pretty confident I can check the homework and still look through it all, so you see what you can do.